Hey guys, I see the formatting hasn't come through very nicely here on my first slide at least for my PowerPoint, so I apologize if it's a little bit messy. But yesterday we talked about the graph of our first direct variation equation, our y equals kx. Today we're going to be looking at the graph of our second direct variation equation, y equals kx squared. Our targets for the lesson are, we're going to continue to find rates of change, only today we're going to find that they are not constant like they were on our y equals kx because it's not a straight line. We'll continue to identify properties of graphs of different functions. Our focus here will be on y equals kx squared, and then we want to be able to graph those functions. We also want to be able to identify, when looking at a graph, which of our equations does it match? Is it y equals kx, or is it rather y equals kx squared? And then recognize the effects of a change in the scale or the viewing window on a graph of a variation equation. So we're going to be doing some things on our graphing calculators today. A graphing calculator, and I'm going to scoot through these vocabulary terms. I can display them, or you can check them out on my blog later on, but I have a limited amount of time here with 15 minutes to post or to make this video. But an automatic grapher is just like our graphing calculator. It's a way that we can enter an equation and have our calculator plot that equation for us without having to take the time to do it on graph paper. The window is what you see on your graphing calculator, and there are some adjustments that we may need to make on our windows to be able to see these various different graphs. So it's the part of the coordinate grid shown on the screen of your graphing calculator. Now the default viewing window is the window that sets it up so that what you see there will go from -10 to +10 on the x-axis, and it will also go from -10 to +10 on the y-axis. And this is the window that's going to work for most of our graphs that we look at here in these lessons. When you graph an equation that's in the form y equals x squared, it always turns out looking like a parabola, like the one I've pictured here from my screenshot from my calculator. So they always look like this. Now, they may open in different directions, not necessarily opening up as you see here in a U shape. They might open down as well in somewhat of an N shape. And you'll notice that these graphs, if I were to draw a vertical line right through the y-axis, we could think of that as a symmetry line or a reflection line. So we say that they are reflection symmetric to the y-axis. And they always are when they're in the form y equals kx squared. We'll be using our trace feature to be able to find some points that lie on the graphs that we graph. And as I mentioned previously, these graphs will open up, or they might open down. Now when k is a positive number, that's when we'll see our parabola will open in an upward direction like this. On the other hand, when k is a negative number, that's when we'll see our parabola will open in a downward direction like this. So here in this example, I'm referring to an example that's in our textbook on page 97, but it's of a parabola, and we're asked to calculate the rate of change. We don't call it slope because we're going to find out that it's not a constant rate of change on a parabola. So as we learned yesterday, what we need to do is just take the difference in our y's and over the difference in our x's. So that's exactly what I did. I took my y's of 56.25 and 6.25, and I subtracted them, and then I took my x's in the same order, 30, My pen isn't working. Give me a sec here, guys. $30 minus 10, and I found that the top part of that rate of change comes out equal to 50 and the bottom equal to 20. So if I reduce that as a fraction, that is equal to 5/2. I showed you that little math frac button yesterday. If I change it to a decimal, that is equal to 2.5 by dividing top by bottom. Well, you can see then when I pick two other points on that graph on example 1 on page 97, I did not get the same rate of change. I was using the ordered pairs 50, 156.25 and 30, 56.25. And this time my rate of change is 5. This demonstrates that on a parabola, the rate of change will be different when I select two different points. The only time we have a constant rate of change is when we are on a straight line. So here is another slide that didn't come through very nicely, so I'm going to pause and rewrite these. Okay, so here they are. I want to graph on the same coordinate plane the equations y equals x squared, y equals 3x squared, and y equals 1/3 x squared. And so what I did was I went to my y equals window, or y equals function button, which is the very far left button underneath your window on your calculator. And in y1, I typed x and then the x squared key. I hit enter or the down arrow, and in y2, I entered 3x squared. So that'd be 3x and the x squared button. Then I entered or hit the down arrow, and in y3, I entered y equals 1/3 x squared, or 1 divided by 3, x, and then the x squared button. To get my standard viewing window, which you see pictured here, all I need to do is hit zoom, and when you get there, you see that 6 is the option for standard viewing window. And you should see exactly what I see here. Now, as they come in, the very first one that you see is going to be the very first equation. So that is y equals x squared. It's that guy right there in the middle that popped up first. The next equation that you see is this guy that comes in here closest to the y-axis, y equals 3x squared. And the last equation that you saw pop into your window was this guy here, y equals 1/3 x squared. So we've been able to graph all three on the same coordinate plane. Let's do the same thing with these equations. And once again, they didn't come through very nicely. So I've got y equals negative x squared. I've got y equals negative 3x squared, and I've got y equals negative 1/3 x squared. So I put them in the same place that I put the previous equations. And to clear the previous equations in y equals, I just hit clear enter for y1, for y2, and for y3. When you hit zoom 6, which again, you'll see a little bit more than I have pictured here, I've zoomed in for my slide, you see these three parabolas pop in the order in which we entered them. So y equals negative x squared is this guy right here in the middle. Y equals negative 3x squared is this guy closest to the y-axis. And y equals 1/3 x squared is the fattest guy. And what I'm hoping you notice is that as k gets bigger, so I'll just say it gets bigger with an up arrow, the parabola gets skinnier. Which seems sort of opposite of what should happen. Whereas when k gets smaller, like the 1/3, the parabola gets fatter. I also want you to notice that when we had negative signs in front of our x squareds, which we had in all of these, the parabola opened down, whereas when we had positive signs, it opened up. So when you look at the equation in the form y equals kx squared, we can tell it's going to be a parabola, that U shape or upside down U shape. They're all going to be reflection symmetric to the y-axis, which means there's a symmetry line that goes right through them in the middle on the y-axis. When k is positive, the number in front is positive, it will open up as I have pictured here. When k is negative, it will open down from the origin as I have pictured here in blue. And all parabolas in the form y equals kx squared sit right on the origin. We say that their vertex is at the origin.